y'all. Today we're going to be going over this problem 3 from exam 2018, I believe. Yeah, exam 2018 on this problem 3 TMZ polarization problem. So this problem here, it tells us that it says, a TEZ plane wave. Again, this is polarization TEZ, not TMZ. Notice that there's a difference. Sometimes they tell you both are in, that we're trying to solve for. Some of them say only TEZ, and some only say TMZ. You have to be very careful about which one we use, because they have different equations, of course. Something else to notice before we get into this problem, I guess I could read the problem here first. It says a TEZ plane, a wave at a frequency, so this is our frequency here, 1.575 gigahertz here, is incident from the air onto the ocean. Non-magnetic. Non-magnetic means mu 0 or mu r is equal to 1. The ocean has a relative permittivity of 81 and a conductivity of 4 Siemens per meter. The angle of incidence is 45 degrees. So this is 45 degrees here. And it asks us, what's the percentage of power that is reflected from the ocean? First thing that we should do is let's write the equation for power, or percent of power reflected. What this is it's going to be this equation. It's going to be, and it's in the formula sheet, the gamma squared times 100. Gamma is our reflection coefficient. Now, gamma can change depending if we're talking about TE or TM. So we're talking about TE polarization, so we put a TE up here. All right, but what is, gamma TE? What equation does that go with? Well, gamma TE, same thing with gamma TM. It's going to be equal to the impedance TE minus the impedance in the first medium. So the 2 and the 1 meaning which medium you're in. So 2 being the second medium, first being in the first medium. Or I guess not really. I guess I'm thinking of transmission lines, but they're just different values that we need to solve for. So this is the equation, and this one isn't in the formula sheet that I printed out for whatever reason. This is something we do need to know. It's the same kind of equation from transmission line theory. But, this is the equation we need. But another problem arises. Are we using Z2? What are the equations for Z2TE and Z1TE? Well, this is where we have to understand. Are we in a lossless or are we in a lossy medium? In this case, it doesn't tell us. This is something we have to understand. Not really understand, but kind of find subtle hints inside of the problem to figure out, is it lossy or is it lossless? A lot of the time when it's lossless, he would directly state if it is lossless. Sometimes he won't tell you it's lossless, but the information he gives will tell you if it is lossy or lossless. In our case, we're in the ocean. A lot of the time, the ocean is lossy. Another indicator that we're in a lossy medium is that he gives us this conductivity, this sigma value. The sigma value is very important, especially when solving for epsilon RC, because that's our lossy kind of equation. We need epsilon RC, and we have to use sigma, or the conductivity, to find it. If he gives you sigma, or this conductivity value, and he also gives you ocean, a lot of the time it's going to be lossy. He will tell you if it is lossless. If he doesn't tell you, in our case, again, here, if he doesn't tell you what it is, and he doesn't give you the conductivity, I'm going to assume it's lossless, but in most cases, he will tell you. Some cases, he won't. You'll have to do a little bit of problem solving. But anyways, we're in a lossy case, so we're going to be using different equations. In the lossy case, the impedance TE of 2 is going to be equal to eta naught times 1 over the square root of epsilon RC2, so the epsilon RC, I guess, of the second medium, minus sine squared of the incident angle here. the ZTE1 equation is going to be equal to eta naught times secant of the incident angle. So, of course, we notice, zeta, this impedance for TE1 is much easier. So let's just solve it. Eta naught, by the way, is going to be equal to 376.7303 ohms. It's the intrinsic impedance of air. So we have 376.7303 times the secant, or 1 over cosine, of the incident angle. And the incident angle is 45 degrees. All right, and what we get here from this is 532.78 ohms, because we're in impedance. For Z2TE, we have to notice what don't we have? Well, we have eta naught. That's a constant. We have the incident angle. We have sine squared. I mean, it's just a function right here, but we don't have epsilon RC. So that's something we need to figure out. Epsilon RC2 is going to be equal to this. It's going to be equal to epsilon R2, the relative permittivity in ocean, or in the second medium, minus J times the conductivity divided by omega, the frequency, times epsilon 0, epsilon naught, your relative permittivity in a vacuum. So, well, we know epsilon R2. Epsilon R2 is the relative permittivity in the ocean, or in the second medium, to be 81. So we can set that to be 81. Minus J times 4, because that's the conductivity given in the problem, divided by omega is 2 pi times the frequency. Frequency is GPS frequency, or 1.575 times 10 to the 9th hertz, times epsilon naught, which is 8.85 times 10 to the minus 12. And so what we get from this is, if we plug it into a calculator, you just put in here, 81 minus J, 45.67. Unitless, by the way, because, we're solving for epsilon RC here. Unitless. And now we have our value, and now we can plug it into the equation. So we have 376.7303 times 1 over the square root of 81 minus J, 45.67, minus sine squared of 45 degrees. Something is also very important. Make sure you have your calculator in degree mode, not radians in this case. What you end up getting, if you have a calculator that can do this, that can do square roots of complex numbers, what you get is you get a value of 37.865 plus J10 and ohms. If you have a calculator that can do this, you can skip. If you do not, I'm going to take you through the steps to be able to solve this by hand. For me, at least, I don't have a calculator that can do this, so I have to end up solving this by hand, and if you don't know how to, it can be very difficult. If you do already, just skip ahead, find where the part is. Maybe I'll parse the video. But for people that don't have this calculator function, what you can do is you can do 81 minus sine squared. You want to get the real portion and the imaginary portion apart. This ends up getting you 80.5, so this becomes 0.5. I believe that's right? Let me do it on my calculator real quick, actually. That should be right, though. Sine. Yeah, 80.5. So now what we have to do is we have to then take the square root, or not the square root, but do 80.5 minus J 45, put it back into rectangular form, your real and imaginary part, and now you want to create this into polar form. So polar form. This you should be able to do with the calculator. If not, you take the magnitude and take the phase. So you have 80.5 minus 45.67i. Okay, then you find this value, which is 92.55, angle of negative 29.57 degrees. And now when you take the square root of it, you take the square root of the magnitude times 1, and then the angle, half of the angle, negative 29.57 degrees divided by 2. From here, you should get 9.62 angle negative 14.785 degrees. This is, of course, epsilon RC2. This is the square root. Now what you do is you plug this value back in here, not the square root, but in the denominator, and then you go along your merry way. You can then plug it into your calculator like this. So you get 1 over 9.62 angle negative 14.785. And again, you get 37.865 plus J10. So this is how you would do it by hand. Take the square root of the magnitude and halve the angle. Okay, so now that we have ZTE2, now, this becomes very easy. We have our values. We can then plug it into our equation. So 37.865 plus J10 minus 532.78 divided by, same thing, plus J10, your ZTE2, but now we do a plus 532.78. Well, this gives us gamma TE, and gamma TE is then negative 0.8667 plus J 0.033. Our next step here is to find the magnitude, because that's what we want in our reflection percentage equation. And so again, we turn it into polar form. So we get 0.8667 angle 177.84 degrees. So then we take our 0.8667, 0.8667, we square it and we multiply by 100. Let me see here. And what we get is we get a reflection, percentage of power reflection of 75.17%, just about. And that's our answer to part A. Let me make this a little smaller. So that's for part A. And you'll notice for lossy cases, this is the exact way you solve it every single time. For lossless, it's the same steps, except lossy takes a little more time because you need to solve for epsilon or C. But other than that, it's the exact same way every single time. For part B, though, what you need to do for part B is understand the equation for that relates depth of penetration, your K double prime, and alpha. So what you have is alpha divided by depth, penetration of depth is equal to K double prime. And K double prime might be switched with depth of penetration in the formula sheet, but it doesn't matter. Because what you get is alpha is equal to K double prime times depth of penetration. Of course, if you want, what will happen is this will be in meters per meter, or I guess in meters by itself, actually, because you're multiplying by depth of penetration. You'll get meters here. And then to change it into decibels, you need to do what? Multiply by 8.686. So now this turns into only decibels. So you went from meters to decibels by multiplying 8.686. All right, so from here, it's pretty simple here. We know the depth of penetration is going to be our Z value. This becomes 10 meters because we're trying to find the attenuation at that 10 meters. So really what we can do is, instead of putting depth of penetration, we can put Z as our variable if you want. If you're only looking at the formula sheet, I would recommend, this is just like the very last part of exam 2. This is the exact same way you would solve it. To find K prime, though, we need K, because K is equal to K prime minus J times K double prime. We need K double prime, I mean. To find K, though, we use this equation. K is equal to K naught times the square root of epsilon RC2 minus sine squared theta incident angle here, incident angle. And you know what? We've already found epsilon RC squared minus sine squared of the incident angle up here. Remember, we took the square root of it, It's way up here in our ZTE2 equation. So we can just plug it in. We already know. We know square root of epsilon RC2 minus sine squared incident angle. Well, what is that? That's equal to, let me see, 9.62 angle negative 14.785 degrees. And then what is K0? Well, K0 is going to be equal to omega times the square root of mu naught times epsilon naught. So this is 2 pi times the frequency that they give. Make sure in part B, if they give you a new frequency, to use it. In this case, they didn't. So we can use 1.575 times 10 to the 9, this is in hertz, times the square root of mu naught, which is 4 pi times 10 to the negative 7, times epsilon naught, 8.85 times 10 to the minus 12. Okay, so we get for our K0, we get 306.9. Actually, that's not K0. For K0, what we get is 33. From here, very simple, we then multiply 33 times 9.62 angle negative 14.785. Let me make sure this actually gives us the right answer before I say this is the right answer. Yes, okay, cool. So K is then equal to 306.95 minus J81.01. Okay, so that's our K value, but K double prime is what we're looking for. What is K double prime? K double prime is the imaginary part of K. So that means K double prime is equal to what? 81.01. In our cases, we're looking at the absolute value. So it's 81.01. Even if you have negative here, then what you would do is change Z to be negative because you're going in the negative direction. You could always just take the absolute value because attenuation, unless you know your attenuation will be negative, meaning your gain is high, then don't worry about it. Just put in the absolute value of your numbers. What you'll then see is alpha is equal to 81.01 times 10 meters times 8.686. Well, what is this equal to? This is equal to, let me plug it in here, 10 times 8.686, 7,036.53. And don't forget units. We want to make sure we know it's in decibels and not in meters. So we can check our answer, 7036, perfect. Our power percentage, 75.2. Where's the answer? Up here, 75.17. Close enough, you know. Okay, cool. So this is how you would do a problem in the lossy variation. The next video will be a lossless variation. You'll notice how much quicker it goes. But yes, hopefully this made sense. If you have any questions, make sure to comment them or message me in Discord, however y'all want. But yeah, this is the way to do lossy. This is the harder one of the two. If you know the steps, you can do this every single time correctly. All right, so hopefully this helped. I'll see you on the next one.